couple of quick examples for interpretation. Let's just say your applied force is a constant 10 newtons. Kappa is 2 newtons per meter per second quantity squared, which can be reduced down to just kilograms and meters and seconds. Hopefully you know how to do that. There's a kilogram meter per second squared and divide by meter squared per second squared. Get a kilogram per meter. Think about what you got. And let's just say your initial condition now is that V of 0 equals 0. So V equals what? Square root of F over kappa. And F over kappa darn well better have units of meters per second, units of velocity, okay? Okay. Now, of course, you could have tangent. C could be pi or 2 pi, any multiple of pi. Tangent's going to be 0, right? But we kind of restrict ourselves for the arctangent really has a domain that just goes from negative pi over 2 to pi over 2. Okay, and the units are down to up, right? Okay. So staying within that domain, the only one in that domain would be 0. So the only one that correspond to that domain would be C equals 0. Okay, well, the square root of F over kappa, it's going to be newtons over newtons per meter per second squared, meters per second quantity squared. And when you divide that, it's going to give you meters per second quantity squared, so it's going to give you meters per second, right? And this is going to be what? You divide this, you get 5 meters per second. F over square root of F over kappa. Kappa's starting to look a little ragged. Be this, okay? Times the tangent of negative. Okay, well, now you got kappa F over M, right? And the numbers are going to be, oh yeah. Mass, 3 kilograms, okay? So your kappa F is going to be 20 divided by 3. Okay? Let's make it 5 kilograms to get a nice number. Okay? 20 divided by 4, 5 is 4, and the square root of that is 2, right? So it's negative 2. And the units of this, which I'll let you think about because we're kind of out of time, okay, should be per second. Times t. Again, I'm just evaluating these constants here. Okay?
The velocity equals 5 meters per second. You have square root of F over K. Like, why don't we do the square root of
I did the square root of that. F over K gives us units. Oh, yeah, square root of 5, yeah.
that? Okay.
Just thinking about the whole quantity.
Yeah.
5 should be square root.
The units.
I don't mind writing square roots.
Yeah.
There's no reason I should be avoiding it, but apparently I'm just not thinking to do it, okay? So, this is not a very intuitive solution because this tangent is going to approach negative infinity as t approaches pi over 4 seconds. Okay? So there's something wrong there. So you got to look at how to interpret these things. But I believe this is a valid solution. And you know, go by the examples in your book and make more sense out of it. Because what should be happening is as t increases, the argument of your tangent function should be approaching 0, but not happening. I'm not, anyhow, there's a solution. Would give you some problems, work on it, okay? And then think a little bit about interpretation. Now your book, again, is using kind of a fairly unique case of free fall, and this is a more general case. So they have, you know, their force is mg. So this would be square root of kappa g here, okay? That's basically the difference in the notation. This is more general, and I've got to think about this in a more general context. I want to do the general context rather than just the free fall, okay? Just looking abstractly at the fact we've got this equation, okay? We've got case 2, where the drag force is proportional to v squared, and that breaks down kind of into 2 cases, depending whether you have 2 negatives here or a positive and a negative, okay? The positive and negative comes out with a reasonable solution. I'll probably try to bring that out in the problems I say, because I'll make up a couple of problems to clarify some of this, okay? And then look at your book. I'll probably give you a couple of problems out of the book. Okay? Okay, good.